Hello and welcome to our talk ARMageddon, how your smartphone CPU breaks software-level security and privacy. In the beginning, I want to say that if you have a safe software infrastructure, meaning that your code has no bug, this does not mean that the execution will be safe, because the hardware where the software runs on may leak information. And today we want to focus on the CPU cache. Because maybe you have seen in the past that cache attacks can be used for covert communication and to attack crypto implementations. However, they have only been demonstrated on Intel x86 for now, and as mobile devices like smartphones and tablets have become the most important personal computing device in the past, and despite the fact that people thought that those attacks cannot be applied on mobile devices, we wanted to investigate why they don't work on ARM and if we can do something about that. But before that, I want to introduce myself. My name is Moritz Lipp. I'm from Graz University of Technology and I'm a master student and I've just finished my master thesis. If you want, you can reach me on Twitter, write me an email or just come and talk to me later on.
And my name is Clémentine Maurice. I finished my PhD last year and I'm now a postdoc at Graz University of Technology. You can also reach me on Twitter or by email or even later. The rest of the research team is composed of Daniel Cruz, Raphael Spreitzer, and Stefan Mangard, and we are all from Graz University of Technology. And before we delve into the details, we're going to show you a quick demo.
So on the left, you should see the screen of this Galaxy S6, and we have just started up the Messenger app, and on the right side, we have a terminal, and we will start our spy tool. And now Clementine will type something into the smartphone. And as you can see on the right, whenever she presses a character, our spy tool catches that. And also if she presses the space bar, we see that on the right. And at some point, if she may decide that she wants to delete a word or a character, we can also spy on that. So because of that, we can derive the words, the length of the words she types, and spy on the user. And we will now show you how this is done. And as we said, this is no software bug. It's just because of the hardware. So for the rest of our talk, we first give you some background information about CPU caches and about the CPU architecture on Intel x86 as well as on ARM. Then we will discuss the challenges, why those attacks are so hard can be mounted on ARM. And then we will show you how you can solve those challenges. Then we will demonstrate you some attack scenarios, what you can do with those attacks besides the demo. And in the end, we will give you all the tools that we've developed to mount such attacks. And Clementine is going to tell you now about cache attacks in general.
Yeah. So as you may know, we have a memory hierarchy that is composed of CPU registers, different levels of the CPU cache, the main memory, which is the DRAM, and the disk storage. And we have different timings depending on where data reside on. And this is precisely what we're going to exploit in cache attacks. And in particular, the difference of timing between data in the cache and in the main memory. So if data resides in the cache, the access is going to be fast. We call that a cache hit. And if data is not in the cache, then we have to retrieve it from the main memory, and it's slow, and we call that a cache miss. Now, you can clearly see that we have, we can see the difference between cache hits here and cache misses here. And this is basically what we always start to do when we mount a cache attack. We time the cache hit and the cache misses, and then we can have some threshold because we know that we will never have any cache miss below 700 CPU cycles. And then just by measuring the time and access take, we can say it's a cache hit or it's a cache miss. So we also need for these cache attacks to know precisely how the CPU cache works. For ARM and Intel CPU, we have set associative caches. So we have data that is loaded in a specific set, and that depends on some bits of the address. So this is a cache set here. Then we have several ways per set. So this is one way. Here we have 4 ways. And a cache line is loaded in a specific way depending on the replacement policy of the CPU, because usually when the CPU loads a cache line into the cache, it has to evict a previous line to make some room for the new cache line. So the cache line is here, for example, and this is the smallest unit we're going to talk about. So now onto cache attacks. We have different types of cache attacks. The first one is called flush and reload. And here what's really important is that we have some shared memory between the attacker and the victim. So here that can be, for example, a shared library. So the attacker starts by mapping this shared library, and data that is shared in the memory is going to be shared in the cache. So if the cache line is in the cache, it's in the cache for both the attacker and the victim. So what the attacker now is going to do is the attacker is going to flush this shared cache line so that it's neither in the cache for the attacker and the victim. And then he's going to let the victim perform, for example, encryption that the attacker wants to spy on. And then the CPU will automatically reload some data. Now the attacker wants to know if this particular cache line was accessed by the victim. So the attacker then reloads the data and measures the time it takes. And by measuring the time it takes, he can know if it's in the CPU cache, which means that the victim did access this particular cache line. And if it was not in the cache, then the victim did not access. So this attack is actually quite powerful because the attacker can know if the victim accessed one particular cache line, which is usually around 64 bytes. So this was the case in which we had some kind of shared memory. If we don't have any kind of shared memory, we can use pram and probe. So here the attacker is going to start by filling the cache, and then again lets the victim perform, for example, encryption. And again, the victim is going, the CPU is going to automatically load data, and this is going to evict some of the line of the attacker. So here, the victim evicted one line of the attacker, then another line. And now the attacker wants to know if the victim accessed this particular cache set. And the attacker won't know which particular cache line, but he can know if the victim accessed this cache set. So he's going to probe data it previously put in the cache. So here on the first line, that's a fast access because data is still in the cache. And on the second line, it's a slow access because the victim has evicted one cache line of the attacker. So the attacker now knows that, okay, the victim accessed some cache line that reside in this precise cache set. And now Moritz is going to tell you about the differences between Intel x86 and ARM.
So the first thing we need to be capable and find a way to remove an address out of the cache to the main memory. And for this, we need to invalidate the cache line. And we have cache maintenance instructions available, which do that for us. And on Intel x86, you may know the unprivileged CLFlush instruction, which you can use to perform this task. On the other hand, on ARMv7, while we have such cache maintenance instructions, we can't use them because they're privileged. And they need a kernel module to be unlocked for user space. And this is not the case normally. In addition, on ARMv8, we have also privileged instructions, but 4 of them can be unlocked to user space entirely. And the first big challenge there is that we have no flush instruction available on ARM that we can use without any privileges. So the easiest thing which comes to mind is we just fill the whole cache with different data, then we are going to evict our target address and we are fine. However, this is way too slow, so we can't rely on that. We can improve on that by just filling a specific cache set. And as you can see in this illustration, the green block is the address we want to evict, and we just start accessing as many addresses which map to the same cache set as we have ways. So at one point, we're going to evict the target address. Sounds easy? It is easy, but it's only the ideal case if we have a least recently used replacement policy on the cache active. But in real life, we don't have that because we have a pseudo-random replacement policy. And when we do the same thing again, just accessing addresses, it may happen that we just evict the address we have just loaded into the cache. So in the end, our target address will still remain in the cache. And so this approach is also highly inefficient. So the second challenge is that we have to take care of the pseudo-random replacement policy to find a nice way to evict the address still out of the cache in a fast way. The second thing that we need to mount such cache attacks is we need to be able to measure the time it needs to take to load the address. And on Intel x86 we have the RDDSC instruction, which is also unprivileged. While we can access the cycle counter on ARM as well, we can only do that in privileged mode. So this is not easily done in a non-rooted device. And all the previous attacks that have been published required root access on the device, so they're not very practical. So the third challenge that we have is that we need to find unprivileged timing sources which are as accurate as we need to distinguish between a cache hit and a cache miss.
So beside cache maintenance and timing, we also have the cache hierarchy that is quite different on ARM and on Intel CPUs. So this is for Intel CPUs, the modern Intel CPUs. So we have usually 3 levels of caches. Level 1 and level 2 are private to each core, and we have the last level cache that is level 3, and this one is shared. And it's also inclusive, which means that everything that is on level 1 and level 2 will also be in this last level cache. And that also means that shared memory that is shared in the cache across all cores. So we have no restriction on where the spy is with respect to the victim. So the victim might be in core 0 and the attacker can be on core 3. It will not be a problem thanks to this inclusive property. Now on ARM Cortex-A CPU, we have 2 levels of caches now. Level 1 is still private and level 2 is shared, but this time it is not inclusive. And that means that shared memory that is not in level 2 is not shared in the cache. And that people thought that it was basically the biggest obstacle to performing cross-core cache attacks on ARM. So that's our fourth challenge. We have non-inclusive caches. Then we have the cache hierarchy on ARM big little. And here we have not only one CPU, but multiple CPUs that are interconnected by this core link. And we have the level 2 cache that is shared across core, but only of one CPU. So we have CPUs that do not share a cache. And once again, we would like to have no restriction on where the attacker is with respect to the victim. And this is our fifth challenge. We have no shared cache between these CPUs. So let's solve these challenges. We have those 5 challenges. So now flush instruction, a pseudo-random replacement policy, no unprivileged timing, non-inclusive caches, and no shared cache. So I'll start with the first one, no flush instruction. So the idea is quite simple. We're going to replace this missing flush instruction with cache eviction. That actually works well on Intel x86 because we have prim and probe that I showed you at the beginning. This one does not need any flush instruction. And if we have some kind of shared memory but no flush instruction, we can perform a variant of flush and reload that is called evict and reload. So challenge 1 done. Or is it? Well, actually, no, it's not done yet, because eviction can be slow and unreliable unless you know how to properly evict data. And this is kind of our thing in the group. We're really good at evicting data from the cache, and that was, in fact, the central idea of our Rowhammer.js paper. So if you recall Rowhammer, you access the DRAM in some kind of patterns, and then you're going to have a bit flip in one location that you never accessed. So you need to reach the DRAM and bypass the cache to do that. And we also did that on JavaScript, where you do not have any flush instructions. So we're going to use the same kind of techniques that we did for this one. Which leads me to the second challenge, this pseudo-random replacement policy, because evicting the cache would be really easy if it was not for this one. Because the cache line to be discarded is chosen pseudo-randomly. So what we did on kind of all Intel CPUs was accessing only once n addresses in an n-way cache set, such as Maurice showed you earlier. But because of the pseudo-random replacement policy, this is really slow and unreliable. So what we're going to do is we're going to access addresses that fills into the same cache set, not only once, but several times, and with different access patterns. And the replacement policy is supposed to be pseudo-random, so we should not be able to really influence anything, but as we're going to see, it actually works really well. So this is the kind of numbers that we can have with the Alcatel One-Touch POP2. So if we access 48 addresses that fit into the same cache set, we access them one by one. It takes 6,000 cycles, which is quite fast, but the eviction rate is really bad. So the eviction rate is basically how if the line that we wanted to evict has actually been evicted. So here it's actually been evicted in 70% of the cases, which is really bad. We want something better than that. So if we access more addresses, then the eviction rate goes up. We have 96% eviction rate, and it now is quite slow. We have 33,000 cycles. So we can access even more addresses, let's say 800. The eviction rate is no good, 99.10%, but it's really way too slow, 142,000 cycles. So we're going to access these addresses multiple times. And now with only 21 addresses that we access 96 times, we have an eviction rate of 99.93%, and it only takes 4,000 cycles. We can even do a little bit better with 22 addresses, even a bit more accesses. With an eviction rate of 99.99%, it takes 5,000 cycles, and with 23 addresses, then we have an eviction rate that is perfect. We measured 100%, and it took 6,000 cycles. So this is really good, and even the timing is better than the first one. We had a very bad eviction rate. So now I'm pretty sure that this sounded all voodoo. We have different addresses. We access them multiple times. This is the kind of thing that we started to do manually with ARMageddon, but it's really a pain to do, so we fully automated this process. The idea is that we are going to generate a lot of eviction strategies, execute them on the target device, and then we have a lot of log files, and we're going to build a database to be able to compare these eviction strategies. So as the eviction strategies usually depend on the device, because the cache characteristics are going to change from one device to the other, we can find with this method fast and efficient eviction strategies for any device. And this is the kind of thing that we can now obtain with this eviction strategy. So if you have some kind of shared memory but no flush instruction, you can use evict and reload with these eviction strategies. And as you can see, we can really distinguish between the victim access and no victim access. So we can have a threshold, and this is really the kind of graph we want to have. Now for prime and probe, if you do not have any kind of shared memory, you have a bit more noise, but you can still see this peak. And if you put a threshold just after this peak, you can say that roughly everything that is below this is no victim access, everything that is after this is victim access. So it looks a bit more noisy, but as you will see later, we can still mount a very powerful cache attack with that.
So the next challenge that we need to solve is that we don't have an unprivileged timing source. And as I told you, the performance counter can only be accessed in privileged mode. So we need to find something different that we can use to distinguish between a cache hit and a cache miss. And the first thing that we found is you can use the perf interface with the perf event open syscall, which is unprivileged, and we can also access the cycle counter through that. However, on new devices, it's not available anymore. On the one hand, we just can't access the cycle counter, or the kernel isn't built with this module. So it doesn't work. However, we can also use the POSIX function clockGetTime, where we can pass a timer as an argument, and we will have a nanosecond resolution. If this wouldn't be available, we can have a very simple approach by just implementing a thread counter, which is a thread running on a different core, just incrementing a global variable. And this is enough for distinguishing cache hits and cache misses. So we have now 3 unprivileged timing sources that we can use, and they all give us a nanosecond resolution. And this is enough to distinguish hits from misses, as we can see on this plot. So on the left, we have all the timing sources measuring a cache hit, And then we have a huge gap. And on the right, we have the same only for the cache misses. And it's easy to find a threshold in between that we can use for our measurements in the end. So the next thing that we have to take care of, and this is probably one of the hardest challenges, is that we have non-inclusive caches. Because in this scenario, the victim process is running on core 0, and an address is loaded in its first level instruction cache. And our attacking process is running on core 1. And this cache is, for instance, instruction inclusive and data non-inclusive. And this means that the data from the instruction cache here has also to be in the last level cache. And what we can do now to evict the data from the first level cache of the other core, which is private to the other core, is by just filling our own local data cache and starting populating the last level cache. And at some point, we are going to evict the address out of the last level cache. And because it's inclusive, it will also get evicted from the first level cache. And now we were able to evict an address from another core, even if we don't have inclusive caches entirely. So the second thing we need to do, we need to find a way to measure if the other core has reloaded the address. And the solution is that there are cache coherency protocols in place on the CPU, which run all the time, and they allow us to fetch data from a remote core. And the reason behind this is that loading the data from another core is still faster if we need to have a memory access. And as you can see on the plot, while it takes roughly 100 cycles more to load the address from another core, it's still much faster than if we would have to make a memory access to the main memory. And we can exploit this to measure if the address has been loaded by the other core. So we can run cross-core attacks as well. The last thing we need to fix is that we have no shared cache on modern phones which have multiple CPUs, so that there's no shared cache between them. And the answer is, again, cache coherency protocols, because they allow us to fetch data not only from the remote core, but also from the remote CPU. And this is also faster than if we would have to access the DRAM. And while we see here that it's much slower than a local access, it's still roughly 100 cycles faster than if we have to make an access to the DRAM. And regarding that, for performance things, we can exploit the cache coherency protocols which are running all the time. And now we have found a solution for all those challenges. And we want to present you some attack scenarios beside the demo that we've showed you in the beginning. So the first thing you can do is you can build covered communication. So for instance, a user installs a malicious gallery application, and he is not suspicious when he installs this app, because the only permission it needs is to access the images. So it doesn't need an internet access or read the contact data of the user. In addition, the user wants to see what the weather is outside and installs a malicious weather widget. And he is also not suspicious, because the only permission it requires is to have access to the internet. So what if both apps can build a covered channel to communicate with each other, so that the gallery app can send the image to the weather app, which uploads it to the internet? And so if two applications want to communicate with each other, but they are not allowed to do so because they either don't have the permissions or there's just no mechanism they can use, like shared memory, they can use a covered channel. And a covered channel enables two unprivileged applications to communicate with each other, but it does not use any data transfer mechanism that is provided by the operating system. And this evades the sandboxing concept and also the permission system. And because you have two apps which need to work together, this is called a collusion attack. And what we did was we built a covered channel using the cache. So we used addresses from shared memory, from a shared library or an executable, and we transmitted bits through cache hits and cache misses. So as an example, if you want to transmit a 0, the sender does not access the address, and so the receiver will measure a cache miss. If you want to transmit a 1, the sender will access the address and the receiver will measure a cache hit. And using those building blocks, we can build a protocol based on backhash. So we used a sequence number, and also a checksum to protect our payload so that we can check the integrity of the data and can resend data if we are required to. On the other hand, the receiver responds with the sequence number he has already received. And our cover channel works using flush and reload techniques, evict and reload, and also flush and flush, which we haven't discussed. But basically, the flush instruction also leaks timing information depending on if the address is cached or not. So we can use it instead of the reload step. So our cover channel works cross-core and also cross-CPU, and is way faster than any of the state-of-the-art cover channel which has been published. So, for instance, we had a cover channel using the volume settings, and it only got 150 bits per second. Or one using the type of intents with 4K bits per second. So, our cover channel, in the best case, using flush and reload, had 1 megabit per second. And as you can see, when we use evict and reload, it's much slower, of course, because there's much noise, but it's still faster than any previously discovered cover channel. And now Clementine will tell us how we did the demo and how you can use our attacks to spy on the user.
So on our second case study, and for the rest, the attack scenario is a bit different than for the cover channel. Here we do not have 2 malicious applications, but just 1 malicious application that is going to spy on the other benign applications. So the problem is always which address do we want to spy on? So locating these event-dependent memory accesses. So to do that, we had cache template attacks on Intel CPUs, and basically we ported that to ARM. So the first step is we're going to map a shared library or executable. Then we're going to repeatedly trigger an event, and in parallel of that, we're going to use flush and reload on one address. If we have a lot of cache hits, then it means that this specific address is used by the library or the executable. And then we're going to repeat this second step for every address of the library. If then you want to spy on more events, then you just repeat step 2 and 3. So we obtain a cache template matrix, which is basically how many cache hits we have for each pair, event, and address. So if you have a dark cell, it means we had many cache hits. If you have a light cell, no cache hits. We can do that on shared library and also add binaries. So this example is on the Android keyboard. And what's quite interesting in here is to see that we have different numbers of cache hits for different addresses depending on which type of input we had. So here the user pressed an alphabet key, the enter key, the space key, and the backspace key. And if you see, for example, if we spy on this address in particular, the only event that causes cache hits is the alphabet. So if we spy on this one and we had some cache hits, it means that the user pressed an alphabet key. Now we can also combine different addresses. And for example, if we combine these 2 addresses, then we can differentiate between the backspace and the alphabet, because both the backspace and the alphabet have cache hits on this address, but only the alphabet has cache hits on this one. So basically, if we have cache hits on this address but no cache hits on this one, it means that it's the backspace. And we can differentiate between alphabet and backspace like that. And this is basically what we have seen in the demo. So that was now to see from which address we are going to choose to monitor. And now monitoring them using evict and reload. So on 2 different addresses, on the Alcatel-1 TouchPop2, on this text file, you can see that we can really differentiate keys from spaces. So we have very precise timing here, and we have exactly 1 cache hit per space that the user pressed. So we can really see the inter-keystroke timing here. And we can, more than that, distinguish between the keys and the space, because there is one address that reacts only if the space has been pressed. So we have differentiate between key and spaces and really precise timing. So this was an example on the keyboard, but that is really endless possibilities. Just scan all the libraries, and as long as you have some secret dependent accesses, then you will be able to automate these attacks. The really neat thing is that you do not need any source code for that. Just use the cache template attacks. So you can spy and learn about the user's behavior. Other kind of attacks that we can foresee is like if the user turned on the GPS or the camera, for example. Now we have our third case study. We're going to attack cryptographic algorithms using cache attacks. So our use case is the AEST tables, and this one is a fast software implementation because it uses some pre-computed lookup tables. Now, the bad thing is that since 2006, it is known to be vulnerable to side channel attacks. So the attack has been done by Osbeck et al., and it's a one-round known plaintext attack. So you have P the plaintext and K the secret key, and at each round R, you're going to compute an intermediate state. And on the first round, this intermediate state is the access table indices, and it's just basically plaintext XOR secret key. Now, this is a known plaintext attack. So if we are able to recover these access table indices, it means that we have recovered the key because it's just XOR. So this has been showed in 2006. That's 10 years ago. So nobody uses that anymore, right? No. That's actually the default implementation of Bouncy Castle. It uses these T-tables. And we've seen that we can monitor a lot of things with cache attacks, so let's monitor these T-tables entries. Now, the difference between this attack and the previous one is that for the previous one, we had some kind of shared memory. Here, the Java virtual machine creates a copy of the T-table when the app starts. So it means that we do not have any kind of shared memory, so we cannot use evict and reload or flush and reload. But at the beginning, I've shown you we have prim and probe if we don't have any kind of shared memory, so we just use that. And here's the type, the kind of figure that you can have if the attack is successful. So here you have the plaintext byte values, and here the addresses. And the addresses are basically which T-table entry was accessed. And this has been done using a key that is all zeros, and as long as you have this really nice diagonal, it means that the attack succeeded. If the key is not zeros, then you will just have a different access pattern here, but you can, in each case, recover which T-table entry was accessed and therefore recover the key. And now our last case study.
And in addition, we want to show you that you can also use those attacks to monitor the ARM TrustZone. And the ARM TrustZone is a hardware-based security technology which provides you with a secure execution environment and roots of trust. And there are small applications running on it called trustlets, and they run in a secure world in parallel to your untrusted operating system. And they implement things like a credential store or a secure element for payments or maybe digital rights management. And one wants to assume that information which is stored and processed in the trusted world should not be leaked to the non-secure world. However, we find on one smartphone there's a trustlet which you can use to create RSA signatures for arbitrary data. And we measured some timing differences depending on the key that is used. And we had no knowledge about the implementation of the trusted operating system and also not about the trustlet. So we didn't have any source code, and it's not necessarily required to do something without having a source code. So what we can do is we can distinguish between valid and invalid keys that are processed in the TrustZone. And on this plot, you see on the x-axis the cache set that is used, and on the y-axis the mean squared error from two measurements in comparison with the mean over all valid keys. And the black line is an invalid key, and you see there's a huge difference on almost every cache set if you use an invalid key, on the other hand if you use a valid key. And over here you can see you can also distinguish between which key has been used on some cache sets. And maybe you can build more sophisticated attacks on that, because the TrustZone in the end leaks to the untrusted world, and so you can monitor what's happening in the TrustZone. So last but not least, we want to show you the tools that we have developed to mount such cache attacks. And the first thing we did, we built a library to build cross-platform cache attacks. You can write your attack code once and can execute it on x86, ARMv7 and ARMv8. And it implements various attack techniques, where some of them we've showed you previously. And it's open source, and you can download download it online. And all the described examples that we have showed you today have been developed on top of this library. And we also include eviction strategies for the devices that we have used. So you can go and try the code yourself if you have the same device. And we provide you with a very sophisticated example code and good documentation on how you can install and use the library. And in addition, this library also allows you to implement cross-platform rowhammer attacks. And this is the GitHub URL that we have, and you can just go there and download the code. In addition, if you have a device that we didn't have and you still want to mount those attacks, you can use our eviction strategy evaluator. And this is basically the tool which automatically tries several eviction strategies on your phone and provide you with a database that you can use to analyze and find an eviction strategy you want to use. And it's also in our repository. And last but not least, we have also an implementation of the cache template attacks so that you can also use them to find libraries and executables for vulnerable addresses so you can spy on the user like we did in the demo. And we even give you a small tool which you can use to simulate input events so that you don't have to be on the phone and type everything manually. And you find this also in our repository. And now Clementine wants to talk about some countermeasures, what we can do to prevent maybe some of these attacks.
Yeah, so the first thing to know is that we had cache attacks on Intel CPUs for a good decade now, and we still haven't found a good solution to prevent them because it uses this really crucial element for performance that is the CPU cache, and we cannot just get rid of the cache. Doesn't make any sense. So a first countermeasure that had been proposed for Intel CPUs was to have more coarse-grain timers because we really need to to find the difference between cache hits and cache misses, and that is in the order of nanoseconds. So the idea is if we have a more coarse-grain timers that is on the resolution of, let's say, milliseconds, we wouldn't be able to differentiate between these cache hits and these cache misses. The thing is that, as we've just shown you, a thread timer is sufficient to recover an accuracy in the order of nanoseconds. So as long as we had some really true parallelism for the spy, we will be able to have fine-grained timers. So this is really not a good countermeasure. The second one is no shared memory. So if we do not have any shared memory, we cannot use flush and reload or evict and reload. And these are the really easiest attacks we can do and also the most fine-grained. So we can be very precise with these attacks. The thing is that that left us with prime and probe. And we can still perform really nice attacks like we've shown you earlier. So that would still raise the bar for attackers. So that would still be a good thing to implement, especially if we also have the system information that is restricted. So, for example, no access to page map. So in this case, we wouldn't have any access to physical addresses, and that makes the attacks much harder again for prime and probe. Harder, but again, still possible. It just raises the bar for the attackers. Now, I think a crucial thing is that on modern smartphones, we have cryptographic instruction extensions. So using like AESC table implementation, it should not be the case. So yeah, these instruction extensions are still not the default everywhere. This is really bad. Also, if you have a device that does not have these extensions, we also know how to have crypto algorithms software only that do not leak any information. So that should be the case. Now, it's not a system-wide solution, so it still wouldn't protect from spying user behavior on the keyboard like we showed you in the demo. So I think the message here is we know how to protect crypto, so we should do that. For the rest, there is really no satisfying solution. We didn't find solutions for Intel CPUs. I'm not really optimistic that we find solutions for ARM CPUs anytime soon. Now for the conclusion.
So what we've seen today is that all of the powerful cache attacks are also applicable to mobile devices. And they do not require any permission or any privilege. And you can use them to build fast cover channels, to evade the sandboxing and privilege permission system. And you can use them to spy on the user's activity with a very high accuracy, as we have seen in the demo as well. And you can also use it to derive cryptographic keys and to monitor the ARM TrustZone, which should not be possible. So we want to thank you for your attention and welcome you to try our tools yourself. They are all online. And if you have any questions, feel free to ask them or talk to us later. Thank you.